Hello, hello, hello. Hello, students. This is the help video to go over the first part of our Unit 2 project, the drop project. So make sure on the first slide that you type your name right here. That way we know who this project belongs to. Now there are two different options for this project. You can either do the extra credit option or the non-extra credit option. So the extra credit option requires a little bit more creativity. So you're going to build a contraption around an object that is breakable. Specifically, the most common one is the egg, a raw egg. That's why if you Google egg drop experiment, you'll see several ideas for this. All right, so you need to build a contraption around an object that is breakable. Around means it needs to be around. It can't just be on the ground. It has to be surrounding your object. And the goal is to drop the object with its protective contraption from a very large height and for the egg to not break. You could also use a water balloon. You could also use an ornament, as long as it's not an important ornament. Or if you have some other idea, that's also fine, as long as it's something that is breakable. But again, the most common one here is going to be the egg. Okay, so what you'll go ahead and do is just put an X next to whichever one you choose here. If you do choose another option, make sure that you type what that option is right here. Then you'll need to go ahead and tell me where will you drop your object from. Definitely keep safety in mind, as well as if your egg is going to break, keep in mind like cleanliness. So you might want to do it outside, standing on a chair or on a sturdy table, and making sure that somebody is there to supervise and to make sure that you don't get hurt. I do have some students that will climb to their roofs, again under supervision, in order to drop the object. So you want to get as high as possible while still being safe. All right, so you'll go ahead and just tell me right here, where will you drop that object from in its protective contraption. Again, highly recommend that you Google egg drop experiment, and then you can actually see a bunch of different pictures of people doing these egg drop experiments. It just needs to be made of anything that is around your house. So you can see examples of straws, of cotton, of plastic bags, of paper towel holders, bubble wrap, balloons, etc., etc. Okay, so anything that you can use around your house. Now, if for some reason you don't have the supplies to do this, there is the non-extra credit option. So the non-extra credit option is just to choose 3 objects that you can drop, preferably ball-shaped and preferably bouncy. All right, so generally we want them to be ball-shaped and we want them to be bouncy. So again, this is for if you don't have as many supplies at home, you don't have quite that. Everybody has something that they can drop, right? So everybody should have 3 objects that they can drop. Again, preference though is that it's a ball and that it's bouncy. So examples here would be golf balls, Play-Doh balls, soccer balls, tennis balls, etc., etc. And then just type what your 3 objects will be right here. So again, no excuses. Everyone can do at least one of these options in the experiment. If for some reason you really have some restriction though, please communicate with your teachers. What will you use as your drop height for all of your objects? So you need to choose one of these, right? So you can either choose to drop them from 100 centimeters high, assuming you have a measuring tool that measures centimeters, or that's about 40 inches, so you can also do 40 inches high. Or if for some reason you don't have a measuring tool, you can just use your fingers. As long as you use your fingers for every single object, both the starting measurement and the ending measurement. So what you'll do is if you want to use your fingers, all you need to do is take your 8 fingers, ignore your thumbs, all right? Those don't really line up very well. Use your 8 fingers and stack them up, and then you would do that until your fingers stack up 100 times, which is, let's see here, 100 divided by 8, sorry. I think that's what, 100 divided by 8. Yeah, so that's about 12. 100 divided by 4. So let's do 100 divided by, so that would be 25 hands, right? So you would do 1 hand, 2 hands, 3 hands, 4 hands, until you get to a total of 25, right? So 25 hands in total is the same as 100 fingers, okay? Not including thumbs. Do not include thumbs. Okay? All right. So then what you're going to go ahead and do is you're going to drop your first object from that starting height of 140 100 centimeters, 40 inches, or 100 fingers. And then you need to note on the wall how high does it bounce back up on its first bounce. So I recommend just start it at starting height, drop it, and then where it bounces back up to, just kind of put your finger where it bounces back up to. So on the very, very first bounce. Then you're going to go ahead and measure, oops, this should say bounce height using those same units. So either centimeters, inches, or fingers. Okay. Now your bounce height should be less than your drop height. I'll tell you that as a tip early on. Your bounce height should not be bigger than your drop height. It should not be the same as your drop height. It should be less than your drop height. Then you're going to go ahead and repeat that with objects 2 and 3, and that data will eventually go into your results on slide 17. So you'll tell me what's your type of object, where did you drop it from, 100 centimeters, 40 inches, or 100 finger widths. Every single object needs to be dropped from the same height. And then what was the bounce height using the same exact unit, so centimeters, inches, or finger widths. And then eventually we'll go over how you calculate the change in height and how this is related to inelastic collisions. All right, so once you have figured out, answered some of these, you'll get 3 points just for answering either this slide or this slide, depending on which one you choose. Don't choose both, just choose one. But you only get points on this if you do include your actual photo on the slide 4. So you only get points for slides 2 or 3 and 4 if you include your photo. Okay, so you will indicate if you chose the extra credit option or the non-extra credit option, again, just to reiterate and make sure that things are being consistent. And then you need to take a photo of it. Okay, so make sure you handwrite your name on a piece of paper next to your photo before, next to your objects before taking your picture. Otherwise, we don't know if you just plagiarized it. So this is for plagiarism reason. Okay, so taking a look here, you can either take a photo of your object and its protective contraption if you do the extra credit version, or you can also take a video of your object being dropped, and then you can insert the link to the video, or you could actually insert the video here. So you can do insert and insert a video, okay, from YouTube. You can also email or text us, right? So you can email/text the video, right? So, all right, so that's email or text as well. Okay, so let's go ahead and then take a look at if you did the non-extra credit version. Non-extra credit version, you just need to take a photo of your 3 objects. Again, though, your name does need to be next to it. Again, I do need to know that they're your actual objects that you are dropping. Again, preferably ball-shaped, preferably bouncy. Okay, so that's what you will include here is just your photo. Okay. All right, so question number 5 says, in what direction is your object or objects accelerating? See the diagram below for help. Now, this should be pretty easy because your object is falling, right? So your object is falling down, right? And so in that case, you should be able to pretty easily figure out that it is going in the downwards direction. Is that positive or negative? Again, you can see this diagram right here. Then the force that's causing that acceleration, think about what force causes objects. What force causes objects to fall down towards Earth? This is something that we talked about in class, okay? Then what you're going to go ahead and do is you're going to draw and label the force diagram. Again, this is from the force lesson that we did in class. So let me double check what lesson that was. So this was the 2C lesson. All right, so right here, this was the 2C lesson, friction and gravity. This is when we talked about different forces. Okay, in this case, you only have one force working on this. Again, it's the force that's going downwards. And so you would write the force, you would draw the arrow going downwards, and then you would write the actual name of that force right here. So let me go ahead and show you how to do that. All right, so to enter an arrow, you're going to go to Insert, Shapes, and Arrows. All right, and then you can go ahead and draw a downward arrow, right? So we can draw a downward arrow, and then you need to label it, right? So you would insert and text box right here, and draw the text box, and then label it as label your force here, okay? And that's the same force that you should have determined from here. Again, your options for the 4 forces that we learned, the 4 forces we learned were friction, gravity, normal, and what was the other one? Friction, gravity, normal, and applied force. Okay, so you should be able to figure out which of those 4 causes things to fall. All right, so that should help you with that one right here. All right, so let's go ahead and then take a look at slide number 6. Slide number 6 goes over what's the difference between mass and weight. Remember that regardless of where you are in the universe, your mass is always the same. So your mass will always be the same everywhere because mass is physically what you are made up of, the actual matter or stuff that you're made up of, and that doesn't change depending on where you are in the universe, right? So astronauts are still physically identical to when they are on Earth. It's not like they're chopping off their arms when they go to space, right? Your weight, though, is also known as the force due to gravity, and this can change based on gravity, specifically the acceleration due to gravity. So, for example, on Earth, there's more gravity and more acceleration due to gravity, so you actually weigh more, even though you still have the same mass. No matter where you are in the universe, you have the same mass. On the moon, you have less gravity, so you weigh less, and in outer space, there's no gravity, so you actually weigh nothing. So for the example, this guy right here would weigh 0 newtons in outer space. He weighs 92.59 newtons on the moon and a whopping 560 newtons on Earth. But no matter what, his mass is always the same. It's always 56 kilograms. Okay, so that should help you with slide number 7. It says if you were to take your object to the moon, how would its mass change and why? So based on what we just did on slide 6, you should be able to figure out your mass on the moon. Would it be less than, more than, or the same on Earth? And explain why. And again, we have that definition on the previous slide. Okay. If you were to take your object to the moon, how would its weight change and why? We just talked about weight, right, and how that changes on the moon. Right, so you would say weight on the moon, would it be less than, more than, or the same as on Earth? Remember, weight is related to gravity. So in your explanation, you should explain. So your explanation should include how gravity affects weight on the moon. Okay, and again, that is what we just went over on the previous slide. All right, so now going ahead and taking a look at slide number 8. Slide number 8, you actually need to determine the mass of your object. If you're doing the non-extra credit version, you obviously have 3 different objects, preferably balls, preferably bouncy, but you just need to choose one. So just choose one of your objects, and you would put it and tell me what is its mass in kilograms, okay? Now, again, in the US, we don't usually use kilograms, so there are a couple different options to figure out what the mass is in kilograms. So if you have a light object, you can use a kitchen or a food scale. And then that usually measures it in grams or ounces. And then just Google the number of grams to kilograms. So for example, if I go to Google and I want to find what is 10 grams, here let's do what is 17 grams in kilograms. All right, and go back here. It'll tell you that that's 0.017 kilograms. Okay, same thing if I do 17 ounces in kilograms. It would tell me that that's 0.48 kilograms, okay? So just Google your number of grams to kilograms or your number of ounces to kilograms. Same thing if you have a heavier object, you can measure that on a regular scale, like you would measure your weight, and just do pounds to kilograms. So 17 pounds in kilograms would be 7.7 kilograms, okay? Other options are you can just Google what is the mass of something, right? So for example, if you have a water balloon and you put in 1 cup of water into the water balloon, you can Google what is the mass of 1 cup of water, and it'll tell you right here in grams, right? So 236.5888 grams. Again, I do need it in kilograms though, so you'd still want to make sure that you want to convert it, use Google to convert it to kilograms. So you can take this number and to kilograms. Kilograms. Okay, and so that would be 0.236. Okay, so that's another option. And finally, the final option here is I do have several common measurements. So if you're using a large egg, just know that small, medium, and extra large eggs have different masses, but you can also look at the nutritional data on the back of the carton, and it'll tell you how much a egg weighs in grams, and then again, just Google grams to kilograms. Easy peasy. Golf ball tells you how much that's about. Soccer ball, basketball, tennis ball. Again, these measurements are fine for you to use if you don't get an exact measurement. If you do need help, let me know, and obviously come to office hours and we can help you figure out the mass of your object in kilograms. Then what you're going to go ahead and do is you're going to calculate the weight. Again, weight is including gravity. Mass will always be the same. Kilograms is always the same. But when we talk about weight, we actually do need to include gravity. So the acceleration due to gravity on Earth, I'm going to tell you right now, is negative 9.8 meters per second squared. So this should be negative 9.8. So please copy this number. Negative 9.8 meters per second squared. All right, and so all you need to do then is to calculate the force due to gravity, or your weight. You need to take the mass that you just got from the previous slide, right? So we literally just got mass from slide number 8, okay? And multiply it by this negative 9.8, negative 9.8, okay? And that will give you your force due to gravity, or your weight, and the units are newtons. Don't delete the units, make sure that the units stay there. So that will give you your weight. Okay, question number 10 is asking about how is it that even when we have Newton's third law, where things experience equal and opposite forces, they don't necessarily experience the same type of motion. And the reason for that is because the mass of each object matters. Okay, so even though forces are equal and opposite, this is not the same thing as the acceleration and motion that they might experience, because the mass of the object matters. Examples here are, in our boat example, we talked about how if you have a small mass, right, and you jump off a boat that has a big mass, a large mass, you will move a lot, but the boat will barely move. That's because even though they have equal and opposite forces, mass and acceleration are inversely related. So the person with small mass will actually have a really, so the person with the small mass will actually have a really big acceleration. So your jumper moves a lot. Whereas down here, the boat has a very large mass, and the result is the opposite. They end up with a small acceleration. Okay, same thing over here. The more mass an object has, the less acceleration it has, and vice versa, even if they have identical forces. So same thing with our cannonball. Cannonball has a small mass, but a very large acceleration. It shoots really far and really fast. And your cannon barely moves at all, right? It has a very large mass, and so it barely accelerates at all, even though they have equal and opposite forces. So this is going to be related to the next slide. So let's go ahead and take a look at Newton's third law. Newton's third law says an object's mass is smaller than, the same as, or larger than the Earth's mass. This should be pretty easy. The Earth is huge, right? The Earth is gigantic. So you should be able to figure out pretty easily if your mass of your object is smaller, the same, or larger than the Earth. Same thing over here. This is just the reverse statement. Again, our gigantic Earth, is it smaller, the same, or larger than your object's mass, right? So for a hint, your object is definitely smaller, so therefore the Earth should be what compared to your object? This is the opposite, right? So this one should be the opposite. Opposite, okay? So therefore then, your object's acceleration, what will it be? Smaller than, the same as, or larger than? And again, we talked about this. If you have, right, even if they have equal and opposite forces, when your object hits the Earth, think about how your object moves a lot, but the Earth barely moves at all, right? So again, this is related to the fact that even with opposite and equal forces, okay, the mass matters, right? So if we have a large mass, then we have a small acceleration. Or if you have a small mass, then you will have a much larger acceleration. Again, this is like our cannon or boat, and this over here is like the actual cannonball or the jumper. Okay, so that should help you figure out what's going on this slide as well. But mostly you should be able to think about how the Earth barely moves, right? The Earth barely moves because it's huge. All right,